Okay. We're going to do a little bit on chapter 6. I'm going to start out. This is the equilibrium model. And all this stuff. Let me move this. Now, in chapter 6 is dynamics, which is motion along a line. So we'll do dynamics, motion along a line. And so 6.1 is going to be on the equilibrium model. Now equilibrium, as you should know, and hopefully I'm in the frame, let me check. Okay. Yeah. The equilibrium model, when something's in equilibrium, it's balanced, like all things should be according to Thanos, right? Well, this can get really deep. When I was at Charlotte, I taught a course called statics, and in statics, you look at these. Now, it's not dynamic. You look at equilibrium, but you look at things in equilibrium and do not move. That's a whole semester course. In dynamics, you look at, which is another whole semester course, which is basically this chapter and a couple others all in one whole semester. You look at systems where you have lots of forces on things, but it makes them move. In statics, lots of forces are on something, it doesn't move. Okay? It's in equilibrium. Well, not always in equilibrium. Here, this first section is going to be when it's in equilibrium. And that'll then lead us to what it would be when it's not in equilibrium, which is really dynamic. So 6.1 is going to be on equilibrium model, which is statics. It's a term in mechanical engineering classes. 6.2 is dynamics. We're going to do a little bit of 6.2. We're going to do some on 6.1 today. And then we're going to do the rest of 6.2 and 6.3 in class on Friday. So what is the equilibrium model? And they do a whole tactics box on it. Model 6.1, they call it. I'm going to look it up in your book. And what I'm going to try to summarize that. And basically what I'm going to say is, when something's in equilibrium, the sum of the forces, and this is all those forces, equals 0. So what does that mean? That's in a vector sense. So that means, i.e., the sum of the forces in x equals 0, sum of the forces in y equals 0, sum of the forces in z equals 0. So of course you can break force down to x, y, and z components. Alright? If the sum of the forces are 0, what does that mean? No net change in the motion. You can still be going in cruise control, you can still be moving, but there's no net change when it's in equilibrium. Because cruise control is an equilibrium state. Because your velocity is constant. You're not changing your velocity, you're not accelerating. Okay? And you can do all sorts of problems with this. You know, bridges, they have a thing in your book, bridges, towers, take a tower and you pull guide wires down from it. Like radio towers and stuff. What's the force in each one, tension in each one of those? You can have systems like pliers. Some of the forces are 0. And in that class, you also do torques. And we haven't talked about torque yet, which is really like rotational force. They also use that some of the torques is 0. This one with just forces, lots of times in bridges you see, or when you're pushing on things, systems where it's not moving, but you want to know what the forces in each member are. Now, the book uses an example about forces on a kneecap. So for you athletes, it might be interesting. The problem is the way they do analysis, they end up with 2 equations, 2 unknowns, and they get it with sines and cosines. Yeah, you need to know how to do that, but I think it goes almost too much into the math on the analysis side, and you lose the physics on it. So have that for reference in case I put something on there like that. But I'm going to really look at example 6.2, towing a car up a hill. We've talked about ramps a little bit before. We did them in lab. And so I think this is more applicable to what you understand. So let's look at 6.2, example 6.2, towing a car up a hill. Sometimes if you have older vehicles like I had for a lot of my life, you get them towed every so often. And in this case, they're towing it with a rope. Now, what's so funny is, years ago, I was working for a veterinarian, and he needed to get this farmer's farm. And it'd been snowing, and it was up in Caldwell County, and he lived up in the hills a little bit. And this little Toyota he had would not make it up the hill. It just would not. I was like, Doc, what are you going to do? He's like, I got to get to this farm. He's got trouble with the cows. I got to go see the cows. I was like, well, what are you going to do? He said, well, hang on. He actually had we call it a come along. Basically, it was something you wrench things out. And he used it actually to pull baby cows out of mama cows that were breached. In other words, in the wrong direction. And I got stories on that. 3 I saw. Not good stories. Disgusting, actually. But he didn't breach a baby cow out of a mama cow with this. What he did, he took that come along and we had me go attach it to a big tree at the top of the hill. It wasn't a big hill, but it was enough he couldn't get up it. And the cable on that was just happened to be long enough we were able to get it all the way down to his vehicle, attached it to the frame of his vehicle in the front, and basically, now I was 16. He was like, do that come along. So you take it, you do this. You do this, and each time you're doing this, you're basically pulling it up the hill. It's got a mechanical advantage here, but still. And I tried, and I got it where I could. And I was like, I can't do it anymore, Doc. Doc was a big man. He was about 6'4", about 240, and long, lean, strong guy. He was like, Doc, what's the matter? Well, he had fun with it, but so he gets up there. Even he was sweating a little bit. He was able to get the car up far enough up the hill. Over the icy patches we were at, and we went along. But seeing this brought back those old memories. So hopefully you can visualize in your head kind of what's going on. So let's look at this towing a car up a hill. So it says a car with a weight of 1,500 newtons. Force of gravity on that car is 15,000 newtons. I'm sorry. Divide that by 4. That's about 4,000. Pounds. So that's a reasonable car. A little less than 4,000 pounds probably. So that's a reasonable car. It's towed up a hill. It's a 20-degree angle. Now, 20-degree angle hill is actually really, really steep. You don't think it is, but if you saw a 20-degree, like a 20-degree road, that's really steep. You can't legally do roads more than 8 or 10 degrees. I had a buddy of mine, civil engineer, was telling me on public highways that there's actually an angle limit. It's nowhere close to 20 degrees. He does 20 degrees, he said no friction, and the tow rope, the tension, force in the tow rope maximum is 6,000 newtons. In other words, if it gets more than 6,000 newtons, pop, that steel cable will break, or whatever cable it is in this one will break. But 6,000 newtons, it's about 1,200 pounds. That's probably still nylon or something. You do nylon at that. Steel cable should be able to handle that. So list our nodes, let's draw a picture. Here's the car, and vroom vroom. Okay, that's the car. It's one of those Nissans that look kind of weird. You know what I mean? With this whale tail. But the guy put a whale tail from a Porsche 911 on the back. Alright, so there was a rope towing it up the hill. That is 20 degrees. So that's our diagram. Let's do a free body diagram now, which we talked about before. So we make the car into a point, and we have a tension is going to be up the hill. That's a force up the hill. That's the tension in the rope. We'll just call this tow rope, just to be consistent. Gravity's pulling down. Whoops. Let's just call this force of gravity. I haven't told you it's mg yet. And there's actually a normal force on there as well. So those are the forces on that card. So what we're going to need to do is find out the force in that tow rope. Max, but we want to know what is force on the tow rope real. What it really is. So to do that, we're going to sum up all the forces. The only thing we can do so far that tells us is, look at the sum of forces in X, sum of forces in Y, sum of forces in Z. We're not talking about Z, because Z would be out of the board in this case. So let's just look at X and Y. So what we want to do is look at forces in X and forces in Y. Now I'm going to do something similar like I did before with projectile motion. Because I have independent axes, I'm going to look at all the forces in X on this side and all the forces in Y on this side. All right? And so to do this, we need to really think about a coordinate system. Now, we got a coordinate system, vertical. We found, hopefully you found in lab, I put the coordinate system up the ramp. It made life easier. So let's do that. And you want to call it this way positive or negative? Easier if we call that way positive. So let's call this positive X. We'll call that positive Y. Of course, that's negative X and negative Y in that direction. I'll put them in there just for completeness. Okay. Now, what we got to do, and this angle here is 20 degrees. Somebody label this angle. Now, if that's 20 degrees, which angle here is going to be 20 degrees? Well, we know that one can't be. And so that one's the complement of it. So if that's 90, that would be 70. If that's 70, so we know that angle there is 20 degrees. See that geometry when you did proofs and all the, side angle and all that stuff? It actually comes in to be useful. Oh. Well, we couldn't have side angle, yeah, because we know what that spells the other way, right? That was one of the ones that didn't work. We had fun with that, remember, geometry. So it'd be side angle side. That one's valid for congruence. Side angle, or you could do an angle side. That didn't work. Similarity maybe, but not for congruence. I can't remember if it was for similarity or not. All right. So let's look at this. So let's look at some of the forces in X. So in X we got the tow rope. So we know that some of the forces have to be 0. So we got the tow rope, and we don't know what that is, okay? Now if that's 20, what we can do, is there a component of this that goes down the hill? Well, yeah, because that's a vector. We can break it down into X and Y components. We know that's X and that's Y. So what we can do is we can call this the X component of that tow rope. That's a right angle there. This would be the Y component. That would be the X component. So the Y component, compared to 20 degrees, that's opposite 20 degrees. So that's sine. So the Y component of, so this would be black, minus the force of gravity Y component. Well, that's going to be the tension minus sine. So we'll say sine of 20 degrees, opposite over hypotenuse. Opposite is the Y component and of G, and that's just F of G, and we know F of G is 15,000 newtons. So what is that Y component of G? 15,000 newtons times the sine of 20 degrees. I ran out of room. I'm trying to save my space just in case. So I can put 15,000 newtons sine 20 degrees right here. Okay. Now, I can look at my Y components. And in Y, I've got the normal force, which we don't know what it is. Normal force, that's positive. It's going to be minus, the Y would be down this way. So That'll be F sub. I put Y here. I am so sorry. I messed up. My bad. Forgive me. That's X going down this way. That's an X component. That's X component. That's X component. It's been a long day, by the way. That's the X component of the weight, is this direction. I even messed it up right there. That is the Y component, and that's the X component of it. Okay? Hopefully I didn't confuse you. X is down this way, component. Y would be down this way for that force of gravity. Okay? So in Y now, we get the force in newtons, the normal force, that's the normal force. We don't know what it is though, but it's there. Minus, and this is going to be F of Y. So F of Y would be this one. So we say the cosine of 20 degrees. F sub G in the Y direction, all that equals 0. This would be 20 degrees. The cosine is adjacent over hypotenuse. So it's the Y component of F sub G over 15,000 newtons. So F of Y equals 15,000 newtons. The cosine 20 degrees. And I don't have my calculator with me, so I'm just going to stick it back up in here. So we say the normal force minus 15,000 newtons, cosine of 20 degrees equals 0. Oh, I can just move this to the other side. So I can find the normal force. I can feel how much it's pushing up off that. The car is pushing down on the ramp perpendicular this much, so it's not pushed up with the same, that normal force. 15,000 newtons on the cosine of 20 degrees. Ooh, I can put that in the calculator and solve it. Yeah. That's going to be, 12,000, 13,000. I don't need that. I did that to help you out because we're going to need to do that later. I don't need that though for this problem. I just need this one. That equals 0. And this one, the sum of the forces, sum of the forces in Y equals 0, sum of the forces in X. So I just move this to the other side the same way. Say the tension force in that tow rope, that tension force, is 15,000 newtons times the sine of 20 degrees. Now the sine of 20 degrees. And 15,000 times the sine of 20 degrees. According to the book, that's 5,100 newtons. And that is right, we've done it in the past. I remember. So it really is 5,100 newtons. Does the tow rope break? You can hold up to 6,000. It's only got 5,100. It's probably good unless it was really bad manufacturing tolerances. You know what they say, if it's manufactured on a Monday, everybody's coming to work, hangover. If on Friday, everybody wants to get off of work, so they're just doing a crappy job just to get it done. Not as bad as it used to be, but there is some validity in that. Unless it's a Monday, Friday tow rope, or just somebody didn't care, but the probability is with the way we do a quality control now, that's not going to happen. It's not going to break. Not break. And if you're using a tow rope, that's good, because if you're standing behind it, thinking, that tow rope ain't going to break, and it breaks, pop. You better run real quick. Now, the question is, that's a static system. In other words, it's constant velocity going up the hill. It is moving, but it's constant velocity, no change in motion. When you get to dynamics, which is section 6.2, you're using Newton's second law. What I want to say is, I'm going to just erase this part right here. 6.2, using Newton's second law. You still look at these forces because, you're resolving forces is the term. You're looking at forces coming in on each other, multiple forces. But now those multiple forces are causing motion. It's causing something to move. And if it's causing something to move, what relates forces and motion? We've only studied one thing. And I said it is fundamental, and it is, to relating forces and motion. That is Newton's second law. So, for systems not in equilibrium, the sum of the forces is not equal to 0, then motion occurs. And what's the only thing I gave you and that we've studied that relates how forces make things move? Newton's second law. So in this case then, the sum of the forces don't equal 0. The sum of the forces then must equal mass times acceleration. And this is acceleration of the object. So once I do it the same way. I sum up all my forces in x, sum them all up in y, sum them up in z, because I can write this the same way and say this is the sum of the forces in x, gives me my acceleration in x. The sum of the forces in y gives me my acceleration in y. The sum of the forces in z, I'd be out of the board in this case, but we're not doing it, but sometimes you do. The acceleration in z. Put it down here, because that's a subscript. Don't want you to confuse it as max. It's m mass times acceleration in the x direction, mass acceleration in y, mass acceleration in z. You may ask, well, why don't we have components of mass? Well, because you can't. Mass is just how much something resists motion. If it resists so much in x, y, and z, in x, y, and z, that's constant. Now, you could say, well, what about friction? Friction's another force. This is just the object's resistance to acceleration. Now, in this model, that doesn't have a component. In a real object, you could, but for what we're doing, that's way further down the line than you want to do. And matrices would probably be needed to help solve this, to be honest, possibly tensors. Now, that's this situation. They do an example in your book. Speed of a towed car. They have a car that's being towed. You can take this problem we just did and do it the same way. Because what I can say is, now it's at a constant velocity. We know the tension in the rope is 5,100 newtons. Now we get the car up on a flat and it's moving at 50. Now it's 5,100 newtons constantly being pulled on it. Now, whatever's pulling on it would have to keep going faster, because it's now going to make this car accelerate. It's going to move and it keeps a constant force on it. Then you would say 5,100 newtons would go here, say in x. You know the mass of the car, you find acceleration of the car. Once you find the acceleration of the car, you can find how far it moves, how fast it's going. Remember those motion equations we did. We'll refer back to those to solve problems here. The problem they do in the book is actually a decent problem. Example 6.3, I'm going to say put in your notes. In class on Friday, put this in your notes. I want you to have done some work with this, because in class on Friday, what we're going to do is look at altitude of a rocket. You guys are going to be flying rockets pretty soon, and we're going to mention the project here on Friday. But a rocket, when it flies, has two phases. One in a boost phase, when the motor's pushing it, then in a coast phase, when it's not. We're going to solve the problem of neglecting air resistance. How high would a rocket go? Looking at how long the motor burns, and with how much force. And then, based on that, we'll look at how high it coasts up. Because the first part of the problem, the burn phase, if you think about it, is a dynamics problem. It's some of the forces. We've got to look up forces and how much they cause motion. That's Newton's second law. We've got to do this for the boost phase. But the coast phase is throwing something in the air with an initial velocity. The rocket just gives us a whole lot more initial velocity after the boost phase of that motor. Because now it's just coasting, just like that marker is. I'll throw it up in the air. You could say I got a rocket engine as an arm, right? So I have a fast bump. No, not really. But this is mimicking a very, very weak. When I throw it up in the air like that, it's a very weak rocket motor. So I could actually mimic it, take my hand away, put a very small rocket motor here, have it burn for half a second or so at a very low force, and it could project it at the same height because it's the same effect. Okay? Exact same effect. That's what we're going to do. So put 6.3 in your notes by Friday when you come to class or when you listen to it watch it on Zoom. And then we're going to do this one. And if I like this and spend a whole half a class probably to do this problem, something like this just might be on a test. Okay? Thank you very much.